Hey, good morning, all. Good morning, friends. Yeah, I think weekend morning. Not everybody has joined yet. I see only 16 members. Hey, good morning, Naveen, Pravesh, Sheikh, Pratibha, Anil, Sheila, Bharadwaj. Hey, good morning, guys. Yogesh, Gaurishri, wonderful. I see more and more people joining in. Yeah, hope you're able to log in. Oh, sorry, see the screen. Let's see the poll. Wonderful, 100%. Okay, let me ask another question, okay? Just for fun, before everybody joins in. Enjoying the new NLP sessions, very helpful. Yes or no? Wonderful. I think the efforts that we put in are making some sense. Oh, no. Hmm. I didn't expect that. These are not part of your regular sessions, friends. These are additional sessions that we are putting in. We are going in detail, in depth into NLP and discussing, which will not be done. I mean, it's more like a webinar series that we are doing. So it's not part of your regular sessions. I'm repeating. Because we'll not be doing it again and again, so I wanted everyone to join into this, tune into this particular program. Yeah, probably once you learn more concepts, you would try and gain some insights into the subject. But yeah, I think one or two people. Should have been two questions, okay? Different questions? Okay, Brett, Pratibha, yeah. Okay, whoever did not enjoy it or whoever have trouble in understanding these things, probably you can connect with me offline. Hmm. All right, one more minute and we'll start. I wanted to see more number here. It's very less. Okay, hope everybody has created their developer's account in Twitter. We'll be doing it the same code that we have done in Python. Today we will be doing it in R. Okay, and we'll try to do diagrams that we have not done, the word cloud, all those things in Python. And of course, in R, we will do something different. In Python, we'll do something different so that we'll cover multiple aspects. Sheikh, you're still not able to. Um, I think the justification part is something that you have to really look into. That's the only thing which generally helps. Yeah. Recap would be done tomorrow, Sheikh. Today we'll not be able to do the recap, but let me touch base on things that we discussed till now. But yeah, as I said, there's so much of things to be covered. Right? We probably will do it tomorrow. Okay. I think it's good time to start now. We'll begin. Okay. So we started dealing with text mining, right? So why it is important to deal with text mining? Start moving up. Yeah. So any data, right? As a data scientist, we will have to mine the data, right? Churn the data. We call it as data mining process. Under this data mining process, you will have textual data. Text data is also one type of data, right? So we have to explore this text data in a different way. Why? Because it is unstructured in nature. So let me go to the mind map. If you see this, did I put it here? No, where did I put that? Yeah, unsupervised learning, text mining. So when you're dealing with text data, we need to understand one thing, that this text data would majority of the cases would be unstructured, right? So if you have already done supervised and few of the unsupervised or unsupervised and supervised, if you're familiar with those machine learning algorithms which help us churn the data using this equation, similar equation may not be directly be applied here just because the data is unstructured. So what we are doing here, we are first trying to structurize the data. Before structurizing, remember, just like any other process would remain same. For CRISP-DM, we are saying that understand the business problem, then look into the data, that is data collection, then we do pre-processing. Important. So we are getting the data. It might be web extraction or it might be some other mediums that you're receiving the data, but the data is in unstructured format, the text data. And we learned about the feature engineering or feature extraction. We learned about splitting the text data, space delimiter logic, right? So and we basically call it as tokenize. So we tokenize and then extract the meaningful features after filtering or cleaning the data, right? So we learned about tokenization. Different techniques of tokenization is what we learned. Then we have also learned about cleansing, using stop words, right? Using various other special characters to clean the data, unwanted data. We filter the important data out and we'll start using it. Then feature extraction. Feature extraction is nothing but taking the keywords. This is vectorizer, count vectorizer. We also call it as bag of words. This is nothing but your feature extraction step. And when you do bag of words on entire data, you get DTM or TDM. This is the arrangement. Okay, so analyzing unstructured data, then we analyzing basically means you do all that process, right? This process. Then bag of words is done, and when you do bag of words, you'll get DTM or TTM. It's a matrix representation, which I would call as a key and value pair representation, giving structure to your data. So here you'll get structured form. Then the simplest thing that we can do is using the frequency. Here we'll also get frequency. We'll generate word clouds to perform sentiment analysis. Right? Then there's something called a semantic network. We have not done that. We have done topic extraction, that is topic modeling. We have done that. Lexicons means dictionaries. Using this dictionaries, today we will be doing emotion mining, NER. NER means named entity recognition. That is done using lexicons or parsers, or you also call them as dictionaries. This would be the primary thing, right? When you want to work with the text data, you have to give some meaning to it, context to it. And that context can be done using your named entity recognition. Then we've learned about, here in fact, web scraping should be discussed here. This is to get the data. And then we've learned about pipeline building, pipelining. Then yesterday we discussed about, after word clouds, of course, we discussed about topic modeling. Under topic modeling, we covered LDA and LSA or LSI. Right? And then we've discussed about text summarization as well, abstract creation. So these are all different aspects that we have covered. Right? Let us learn on LSA execution in Python. Okay, we'll try to do LSA or LSI in Python today. And then second half, we will be doing the R hands-on. So let's me first cover LDA and LSI, then text summarization. So first we'll start with LSA, latent semantic analysis, or LSI, indexing. And here we have the library called Genset. If you're not able to execute Genset, then that means package. Pip install Genset. I've already installed it, so I'm importing Genset. From Genset, we are calling Corpora. Corpora is a terminology, or corpus is the terminology which is for your entire text data, raw data. We call it as corpus. Okay, and another terminology probably we need to remember is document. Document is one individual entity in your text data. Collection of documents is nothing but your corpus. So if you're talking about customer reviews, then each review becomes one document. If you're talking about a novel, one paragraph becomes one document, one individual entity, right? That becomes one document. So here we are importing that corpora, and then we are importing LSI model from Genset models. And for pre-processing, we will use preprocess underscore string. Then RE, regular expression. This is used to manage the text data. So I'm defining some custom functions here for pre-processing the data. Okay, so these are all for cleansing. You can use this as is. This would identify all the words, all the numbers, uppercase, lowercase numbers, right? Pattern. It repeats the pattern. See, when you see cap, when you see cap symbol, that means it's basically saying start of your string. From the beginning, look into all the words, all the pattern basically. This is the pattern that you're talking about. All the words, English words which are in lowercase, all the words which are in uppercase, and the numbers. Right? And yeah, R basically is recursive. So it is looking into all the data, text data. Then cleaning the numbers. Here first we are cleaning the text. Here we want to clean the numbers. So all the numbers would be removed. Multiple digits, whether one digit, whether two digits, multiple digits, right? All the digits will be cleansed. This is a custom function that we are creating. Okay. Then we define a custom function called clean, which is basically is a combination of text and numbers cleaning function. So it is going to call those functions that we defined above. Then I'm defining path. This is a function which is identifying the location. File system, basically your system's locations, Windows path directory can be identified using this path lib. Then beautiful soup. Beautiful soup is a web scraping, or right, it's a basically a library which deals with HTML pages. So we are importing that. We've already seen this beautiful soup when we were trying to extract the data from HTML pages. Now, I want to load the articles here. Okay, I want to load the articles. So I'm writing a custom function wherein it looks into the directory and takes that directory as a path and then loads the data into a object, writers. And then it is reading the content which is available in that folder. It could be text files, it could be XML files, it could be different files. In this particular folder, along with the text directory, text data, we also have another format called SGM. It's a markup language like HTML. It's called a standard generalized markup language. These are a different format of files that are present in that location. I think, yeah, this is the data. So you see this SGM data. Yeah, this is your SGM data. It's like a HTML only, markup language. So we need to read the content of this particular file. Okay, you can take any random file. All right. Now let's give that location. Here, let me try and pass that. Okay, let me show you that. Here I am passing my data directory. So we will not pass the files, we will pass directory. Okay. We are generalizing, we are defining a function saying that, hey, when I give you path, make sure you are reading the contents using beautiful soup. Extract all the body. This is to extract the relevant data. Okay. We call it as corpora, remember. Then subfunction again, documents. We are trying to load document. We give the location and it has to load the articles. Then we are preparing the documents. Clean document. Clean is a function that we defined above. Take each document separately and apply document. This is like sentence formation. Then pre-process it For the cleansing, preprocessed string is an internal function, inbuilt function, which is basically doing the cleaning. Then LSA is performed here in this function, right? So dictionary dot doc to bag of words. So one document will be converted into bag of words. This is feature extraction that we are trying to do here. Okay, and on that it will apply the document terms, number of topics, right, from the dictionary. This is again inbuilt. So we are creating LSA model here. Then we are running the process here, LSA, we are running it. Corpora.directory, we run it for all the documents. And then number of topics is 10. You want to segregate the number of topics to 10. This is a custom function that we are defining. Right? So let me execute all of these from here. Yeah, load articles are done. Then I'm extracting documents from all those articles or the raw data, preparing those documents by cleansing it, then generating or creating LSA here. Oops. In order to create, I need the terms separated, right? Terms is nothing but the keywords. Then this is the documents, creating LSA for all the documents. So those are the custom functions we have created. Now here I'm loading my directory. You can see I'm just passing till LSA underscore data. And you can see it is reading the contents. It will take some time to read the contents. A lot of files, right? Along with text data, a lot of files are there. These are all different words. People strings, places strings, topic strings, descriptions. So there are certain names which are given here. It is reading the data from these files. I think it has completed. No, yeah, it has completed reading the content. You can see there are 22 articles that it has read from this particular script, from 0 to 21. 22 files are there. Next, I'm creating or generating your LSA. Articles, comma, number of topics is 5. So you're creating number of topics as 5. LSA process, it is generating this. Okay. Now it is preparing the documents. It's creating a dictionary of words. And then it is calculating, right, those LSA words, topics. Topic modeling is basically being done. We'll see the results once it is generating 5 topics. Let's wait and see. And then, yeah, we'll also have big wait here because it also has to do calculation of coherence. Done. So it has generated 5 topics. Number of topics I'm passing as 5. So on these articles, it has done LSA now. And it gave documents. We can try and see the documents here. It will be a big list. And then we can also see the topics. Yeah, these are the documents. It is breaking down each and every document that it has loaded into, right? You can see 82,000, 76,000, 73,000. Those many words are there, right? You can see this. This is your document, 4th or 5th document. There's so many words, right? So it extracted all these words after cleansing it. and then segregating that into topics. These are different topics, their scoring, and all that is given here. If you say model, it says LSI model. This is an LSI model. Imagine that these are a big set of articles about share market, right, sentiment. So there are a lot of articles which are published, and you want to do a topic modeling on this particular data. This is what we are trying to do now. Okay? For different numbers, words or terms, you have topic modeling being done. Now here we are further proceeding with coherence model. Coherence is like doing a scoring. It's doing similarity score. It's like giving the prediction and saying that, hey, this is correct. When compared to these two, this is better. Similarity score, you can imagine coherence as like a measure of a similarity score. So we are giving this command wherein we are generating coherence model. We are passing the model as this model that we have generated, LSI model. Then the text data is nothing but the documents that we are using, which is cleansed. And we have dictionary as well. Dictionary also we have created, right? Gensim library gives us this inbuilt dictionary. So these are the parameters. Coherence, we pass it as CV. That's a parameter that we pass here. And it gives us the calculations. We have to say how many topics we have to do the coherence calculation for. And run these LSA process for those articles, those number of articles, and those number of topics. And then calculate the coherence for those documents that you have extracted here. This is a custom function. I have defined what coherence calculation will do, and then I have defined the loop, basically start and stop. So minimum and maximum, I'm defining two variables, minimum topics as 5, maximum as 7. This would be your start and stop parameters that we are passing here. So get coherence values for topics 5, 6. It's a range, right? Start and stop, it will not take the nth value. N minus 1 topics would be considered. And let me execute it. It is going to again take a lot of time because it has to generate those topics on that huge amount of documents that we are running here. So it's taking the document articles, then preparing the documents, generating the number of topics. Here, the number of topics is passed. Yeah. Right. Number of topics. Where did we define it? Okay, it's taking from this. Sorry, my bad. It's here. Fifth, 5 number of topics, then 6 number of topics. So it is repeating LSA model twice. Now for 5 number of topics. And then after this, it will do for 6. Along with that, it is also calculating the coherence numbers. And we will be able to visualize that as well. Still executing. When you are trying the code, you may try out with small number of topics. You don't need huge number of data for practice purpose. You can start doing with small number of documents or small number of articles. You can also pass directly your HTML or XML data as well. You don't need to have SGM's markup language files. Simple text files data can also be passed. Yeah, so 5 number of topics with 5 topics is done. came up with LSA model. Of course, it also has calculated coherence values as well, right? Coherence scores. It's doing it for 6 documents now. Sorry, 6 topics now. Probably I should have taken only 10 documents, right? I think it's too much of calculation. Okay, let's wait it out. Yeah, you forget about this one, LSA being done in R. This kind of topic modeling, if you try to do it in R at this range on this amount of data, R would not work. R would crash out. It's a computational heavy calculations which are happening in the back end. The matrix calculations, hope you remember all that. The eigenvector calculations, right? Then we will do SDA calculation for LDA. SVD, sorry. The matrix multiplications are happening. Now my system is a 16 GB, right? System. My system's memory is 16 GB. And if I have 22 documents, it's taking so much of time for one topic and one set of execution with just 5 topics. So you also have to understand on what should be the hardware capability for doing this kind of calculations, right? And this is where we need to have GPU machines, and these kind of calculations, right? These kind of executions are generally done on cloud platforms because it's easy to get GPU machines on the cloud. You use it as per your usage, right? So that's the practicality of applying these things on right, real-time data. There are a lot of challenges. All right, so we have generated the scores, and if you see the documents, yeah, these are all various documents that you get. Yeah, huge. It's printing their entire list, which is not possible to see. Now let us look into the coherence values in a graphical representation. I'm importing matplotlib, and then I'm taking the max tops and minimum topics and maximum topics in the list format, the calculations, the coherence values that we have got, right? And then I'm defining the figure here, the dimensions of the figure and the title, x-axis, y-axis, all those things. So I have only 2 topics, right? So it just gives you a straight line. But if you have more number of topics based on the coherence values, the curve might be right shaky. It might go up, go down, etc., etc., etc. So this is basically the coherence values. Now one function that I have masked here, you can see that, is to generate the visualizations inline. When you create your spider, when you first launching your spider, by default the graphics, the setting would be inline. But we change that to automatic from preferences under the topics, under the tools, we go to preferences, under IPython console, we come to graphics, and here you see backend is equals to automatic. By default, it would be generally inline. Okay. Inline means the visualizations would be there in your console. And in the latest versions of Spider, the plot section is separately given here. If I execute this, let me show you. I'm executing this and then generating the visualization. it should actually show the visualization in the console itself. Look at that. Right? So this is one of the settings. If you want to get inline, then you can do inline. And if you want to get it automatically outside, then you have to change this inline to auto. Okay, this is a setting where we are basically saying line run the visualizations, right? For this matplotlib inline only. The parameter, the argument that you're passing is inline. All right, this is about LSA. Let's do LDA. In this, I'll show you auto parameter. Let me clean this execution because freeing up memory is very important. We have a lot of data which is stored in memory. You don't want that, right? So let me clean this up. And then we are doing LDA, latent directly allocation. Again, this is topic modeling. Here, internally it is using SVD, singular value decomposition. So I'm here in this example, I'm taking a CSV file, extracting data from Twitter for an airline company. I'm calling it as tweets.csv. And the column that I'm reading is text column. So this is your tweets. 14,000 tweets are there. This should be easy because the number of tweets is only 14,000, right? You can select any data, that's absolutely fine. Then regular expression for cleaning. /W, this W means any word. Okay, it could be any word. Then URLs, these are to clean URLs. This links. Then if you have special characters, then use this special characters string. And once I define this, we are creating a custom function here, which would basically remove those things. Handle is the words. We want to clean the words. Then we are cleaning the URLs. Then we are working with special characters. And I'm applying this particular clean function here onto the tweets text data. Text column. Let's tweets.text.apply clean. So this data would now be cleansed. So it is cleaning the data a lot. Yeah, URLs are gone, right? And on each word, it is removing the URLs. Emojis are still there. We have not cleansed the emojis. You might want to do that also. We have learned about the logic of text cleaning. You have to add those steps as well. And anyways, pre-processing string, this particular function is going to help us get that as well. We are applying this pre-processing string again onto the text data and converting this data to a list format. Now you got the list format, cleansed data. So tokenization is done and cleaning of all that data is happening here, right? And it still have special images intact. So you have to research on how do I remove these images in these kind of cases. These are all solved problems. You can try and do that. Then again, importing corpora. And this time from Jensen models, we are importing LDA model, not LSI. We are importing LDA. Creating the dictionary of words from tweets on the corpora. We got that dictionary. The number of topics that I'm going to generate would be 5, but before that, let me get bag of words. So corpus would be my bag of words, yeah, representation like this. So it is counting the frequency of the word. right? It is identifying the word, giving the syntax sequence as 0, starting from sequence as 0, and then it is counting how many times each of that word is repeated. Okay, so it's almost all the words are repeated only once. So this is your bag of words representation. Then I've defined number of topics is equals to 5, and then LDA. These right languages make our life so easy. You don't have to do anything manually here. The number of passes would be 10, passing the data 10 times, and the number of topics is only 5. You can change that 5 to 50 also. Based on your computational capability, you might want to do that. For 5 topics, it's taking so much of time if you observe here. So on the corpus, which has 14,000 documents, or sorry, words or terms, is now generating SVD in the backend and gives us the topics. Now it's taking more time, I guess. Now it should not take so much of time. Okay, let's wait it out. Yeah, when I tested it, it didn't take so much of time. Done. So LDA is performed now. You want to see the topics, print topics, and 5 words will be printed. 5 right words will be printed for each of the topic. Now let us again go ahead and work with coherence model to understand that the scoring is done for these LDA models. So here I'm taking only one, in fact 2, 10 and 11. So max topics and minimum topics is 10 and 11, and generating this coherence scores for 10 topics and 11 topics. Okay, let me just generate for one, but I wanted to show you the graph, so yeah, minimum 2 would be better. You can put it to 20 as well, 10 to 20, your choice. But as I said, right, the computation burden would be too high. The 10 topics is done. Now it is doing for 11 topic. Yeah, done. 11 topics. Now visualization. If I execute the visualization now, I'm directly going to the scores and capturing the scores and generating it. The visualization will be there in the plot section because the same session is going on, right? And the IPython graphics parameter is set to inline in the previous code, right? Here we have set it as inline. So we want to get it back to auto, execute this. Okay, it changes to auto. And now if you execute the visualization, it would give us the visualization outside. This is one way to play around with the visualizations. Again, I only have 2 topics, 10 topics and 11 topics. That's what we have executed for. And you can see the coherence scores are coming down. If you have more topics, more number of topics, the coherence scores can be visualized like this. All right. So this is about LD and LSA. We just have to use the Gensim library, which is giving us LDA models and LSI model functions. And we pass those things and decide the number of topics to be generated. In R, of course, it is even further easier, but we'll not work with such a big data in R. Okay. We will move to R, but first let us conclude the text summarization in Python. Let me clean that data again. For text summarization, we need to import NLTK. I'm doing stop words. Yeah, I've updated stop words. Then counter. Counter is to make sure we count the number of counting basically. Sentence tokenization and word tokenization. These are the two functions that I'm importing. Then we import stop words that we have created here or loaded here, right? So those stop words are imported, and then punctuation, and then largest, n largest, head key. These are a bunch of libraries which are required. Now I'm defining the stop words using punctuation marks as well. Stop words would have 179 stop words, right? I'm adding punctuation marks as well to it. Okay, and I'm creating a set of those words. Minimum word propositions we are generating as 0.1 to 0.9. Now I'm generating the functions here which will cleanse the data, clean the data, and then count the number of words. Word frequencies is what we are creating. Bag of words, basically. That's what we are doing. DTM. Compute word frequencies. This is another way to do that computation. And we are saying number of frequencies should be, if it is greater than this, consider it. If it is less than that frequency, do not consider it. Right? So you're removing those words which are too common or too uncommon, very rare words, not at all used, not at all being used. You don't want to have those words in the text summarization. So word frequencies are generated, then sentence scores are calculated here, scoring mechanism. Using that word frequencies, we are generating values for sentences, and then we are here defining the summarize function. Convert everything into lowercase, then apply sentence tokenization, then word tokenization in those sentences that we are capturing, each sentence separately. Then word frequencies would be calculated on the words that we have extracted, and then scores are generated here. Right, we are calculating the scores and choosing the top sentences. Okay, not all, but choosing only the top sentences which have highest scores. This is the syntax. I mean, this is the custom function that we have defined. And to generate the text summarization, I am loading a file which I have created. Big data file formats. This is one of the blog that I was writing on file formats, different file formats that are generally used on big data. So this is totally customized. I have written this. From that blog, I've taken some data and I wanted to see what kind of summary I would get on this particular data. So I'm loading that. File formats, you can see. The challenges with big data are primarily with storing and processing of huge amounts of unstructured data generated at rapid speeds, etc., etc., etc. Okay. So let's see which sentence would have the highest score in this. File formats would basically give you that. So length of sentences. When we are doing sentence tokenization, it is breaking up the sentences, right? So when you say length of sentence tokenization, it gives us the number of sentences. So I have 22 sentences here. And summarize the file formats. Summarize is a function which is basically giving us the top ranked scores ultimately. This is your customized score, right? So we are by default giving 3 sentences. Here we are giving 3 sentences, right, as an input. So it will give me top 3 sentences. The big data stored in various file formats and Hadoop framework will have a huge impact on the performance, and each file format has their benefits and disadvantages. That's the sentence which is basically giving a abstract. It serves as an abstract for my entire blog that I have written. If I want to take second sentence, big data tools allow us to store all data, all types of structured, semi-structured, and unstructured. So it is giving us second sentence, which again gives us some kind of an insight into the text data. Storage is just one aspect, as we have seen. Another important aspect of big data tools usage is the processing of the stored distributed data. Now, if you have to process the file, then the format of the file is important, right? So like this, it is basically giving us the abstracts. You can say number of sentences is 2. If you say 1 here, it gives you only the first sentence. Right? So this is your text summarization. Text summarization is pretty easy from the perspective of coding. All right. So yeah, these are the LDA, LSA, and text summarization codes. We will also run the word clouds in Python, and I'll also talk about positive word clouds and negative word clouds, right? And bigrams as well. So let us execute all these libraries. We have seen this code, okay? This is to extract data from Amazon. So I'm not explaining this because we have already executed this once. So I'm using Beautiful Soup and trying to extract data from Amazon for the mobile, and I'm trying to extract data from 20 pages. And unfortunately, I got only 8. So let me rerun this just to try and get more data. As I said, there is this issue with respect to the Beautiful Soup library executing on Amazon. Fortunately, you'll not see the problem in R. Anyways, so I have now 90 documents, or you can say 90 reviews have been extracted. Okay, 90 reviews. Though I should actually get how many? 200 reviews. I'm taking that data and writing into a file. All this while we were only reading the data, right? Now, if you want to save this extracted data, then you can use this syntax, that open function with write parameter. W is write, and encoding is UTF-8 standard character set. You will be writing the data as an output into that file called 1plus.txt, and this file is getting stored here in the documents location. This is the default general location that we have. One plus 25th July. This is the extracted data. Okay. Now, I'm converting the entire data into a single string. So wherever there is a space, make sure that space is eliminated and join those sentences using that space only. Right? So paragraphs will be merged now using single space. So it is now created a single string. The entire corpus that we have, right, it is merged into a single string. Though for reading it looks into like different paragraphs, but internally it is a single string. Then I'm importing NLTK for stop words. For cleansing, I'm adding this strings, converting everything into lowercase letters, cleaning the words, cleaning the numbers, and here you can see the data is now cleansed. Right, a lot of characters, numbers, everything's are gone. Everything is in lowercase letters now. Right, and then the words that we have, I mean the strings, the data that we have taken here will now be split into words. Split function is being used here. Split it into words. How many words do I get here? 13,245 words. You can also use tokenize and or different techniques to generate these words. Right? So 13,245 words have been generated. Then I'm using TF-IDF vectorizer. It is going to come up with the vectorized number. And n-gram range I'm passing as 1,3. N-gram range 1,3 means it's basically looking into unigram, bigram. So it captures for unigram TF-IDF values and bigram TF-IDF values. You can decide on how many values you might want to choose here. And now, once I've defined vectorizer, I'm applying it onto my words, review words. And this gives us X. This is your count vectorizer. It's a matrix format. Now the stop words. Now we can use the NLTK stop words that we already have, or this is another way to do it. So I have a set of stop words that I have defined into a file. So this is a custom built stop words. So I dumped a lot of words into it, and I'm defining that this would be my stop words that I want to filter out. So customization. By default, NLTK gives you only 179 stop words. But if you want additional custom words to be filtered out, then you're defining that. So I'm calling stop underscore words here as my string, which loads all those words. But these are like a single string, right? So I'm splitting that based on this new line character to give the words. So 571 words are there in that my custom stop words file. You can generate, okay, your wish. Now, along with these stop words, you might want to add more stop words if you want to. You can always add these words directly into that physical file and then load it, or you have already created this list, right? To this list, you are extending these additional words. Because I'm dealing with mobile phones, which is OnePlus, I'm putting these words as well so that those words are also removed. Now here I'm doing a comparison using for loop. Take each word from IP review words, which basically has 13,245 words, and choose it only if it is not present in these stop words. So you're comparing each word with that dictionary that we created. And if the word is not there, it basically selects. So you're filtering out the word which is present already. And then all the words, filtered words, now I have only 5,000 filtered words, are getting merged together into a single paragraph. Add all the words, join all the words with space. And these are your IP review strings. So cleansed data is available now, right? On this cleansed data, we can use this word cloud function. This word cloud function is available under a package called word cloud. All you need to do is pass the cleansed data here. On this cleansed data, you are generating the word cloud. And this is the dimensions, height and width of the visualization. And the background color for that visualization you're putting as white. So if I execute this and show the visualization here, what happened? I think it's coming here. No? Okay. Now I execute it. Again, it should not take so much time. Okay, I got grid and all those things, additional things are coming. Okay, fine. So these are your visualizations, words, right? Now from this word cloud, you have to basically try and understand which word is important, why they are speaking about it, right? What feature that people are most worried about or concerned about. Those kind of interpretations have to be done from the word cloud. Now we want to do sentiment analysis on top of this. Now if you look at this is a simple visualization on all the words that we have obtained. But out of these, what are those words which are given in positive sense, right? Which of those words are negative? If I can extract that positive word separately and negative word separately, then interpretation becomes much easier, right? But to generate the positive words and negative words, we need again to have a dictionary. Okay, now that dictionary again will be a customized dictionary, just like what you have seen for the stop words, right? Because you might say the phone, I purchased the phone in a hot deal. The word hot in this particular sentence would be a positive sentence, right? It's a positive sentiment. You're purchasing the phone in a hot deal. Then you're talking about an offer. Somebody might say the phone is getting hot for 2 minutes of usage. This is another review. Now here the word hot was used to represent a negative context, right? So for every product, every person, every service, the context might vary for the same word. In the word cloud, we are not looking into the context or named entity recognition here. We are just pulling out the words and then representing the words here, right? So if I need to have positive word clouds and negative word clouds, then I need to have the customized dictionaries here. So I already have those customized dictionaries in place. Positive words dictionary, negative words dictionary. Again, you can create these dictionaries. It's just a manual effort that you have to put. Make sure that these dictionaries are created upfront. For each product, the dictionary would be different. Right? The literature will change for the product to product, right? You cannot use the same literature. So I'm generating a dictionary of positive words. I'm calling it as positive words. Here you see 2006 words are there, positive words. And then I'm filtering those words here which are present in positive words. Choose only if the word is present. So I got all those positive words now. And on these positive words, this is a string that gives us all the positive words. Very few words are there. I'll generate the word cloud on that. And I'm creating a different figure here. I'm saying figure 2. All right. So this is figure 1, which is all the words. And this is figure 2, which is containing only the positive words. Similarly, let us do negative word cloud as well. Again, the same process. This time you are defining the dictionary or a file with all the negative words that you feel would be apt for this particular product. Choose the negative word string. This gives you the negative words. And then on that negative word, come up with the word cloud. I'm saying figure 3. And the background color, I'm changing. I can play around with these parameters. Here I'm saying it is black in color. This code is already shared with you all in the LMS. So this is your negative words. Wrap, lag, lack, disappointed, slow, cons, drain, killer, problem, pathetic. So all these are negative words. So this way you can come up with positive word cloud and negative word clouds. This would help us interpret better. Let us now come up with bigram visualization. So again, I'm importing punctuation. Package punct is up to date, very good. Then I'm loading the inbuilt stop words and the word cloud. I've already imported this, but yeah, let us do that. Here I'm using lemmatization, NLTK package lemmatization, WordNet lematizer. I'm taking that string, the string which we already have, right? Consider everything in the lowercase letter. I've already done that, but just to make sure that we don't get any uppercase letters, we are taking those letters into the words into lowercase letters. And I'm removing the single quotes. Right? If you have anywhere the single quote is there, remove that. Because you might, when you're writing a review, you might want to add 2 words and then write it. So you might put quotes, single quotes, right? So we don't want that. So we're removing that and replacing that with comma. All right. Replacing with nothing, empty. Then we have tokenizer, word tokenization function. I'm importing that for my text. And then considering the text here. Yeah, NLTK text. On the tokens, you are again applying NLTK text. Removing the stop words, removing these special characters, numbers, all those things from your string data. If you have any, which we have already cleansed, so that's not an issue. But if you want to work with the data and do this, if let me do this otherwise. Okay, I've taken this raw data, which has the special characters and all that, right? If I do the text have into the tokenization and then apply NLTK.text, then the data. This time I'm using stopwords which are custom. You can see stop. Hey, how about now? Are you able to hear me? Are you able to hear me? Okay, I think some network issue. So let me repeat the word cloud thing. Can we use dictionary.doc to bow when we extract reviews? Yeah. These are different ways to do the word, bag of words, Satya. You can absolutely do that. Yes, Bharadwaj, you can use Colab. Ranganath, yes, you can use Colab. GPU systems would always be good, yeah. 4 GB, forget about it. It's gonna take the entire night shake. Okay, voice is sure. All right, yeah. Yeah, now are you able to see the screen as well? Is the screen visible properly now? Okay. All right. So I was talking about bigram here. So we did positive word cloud and negative word clouds. Yeah, positive word clouds and negative word clouds. Oh, is it? Seems your mic is plugged out, Shreya. Are you not able to hear me? Can hear, right? Okay. Okay. All right. Oh, I'm assuming you got this positive word clouds, corpus, negative word clouds. Okay, so we'll start bigrams. Bigrams, first loading the punctuation marks. I mean, these NLTK, we have punct. This is the library which gives us the punctuation marks. Then I'm loading the word cloud and stop words functions. And defining word net lemmatizer. This is to lemmatize your words, stemming lemmatization, remember? And then I'm converting my original data, IP underscore v string that we have here. Yeah. This is the original data that we have extracted from Amazon. Right? I'm loading that as to convert everything into lowercase letters. So my text is now the lowercase, right? Lowercase. This is the data. Everything is lowercase now. But we have to clean the data, right? So in order to clean the data, first I'm removing a single quote. That's quote. Yeah, not the internet here. I'm trying to. How about now? How about now? Are reconnected using a different internet? Better? Okay. Yeah. All right. Yeah. Wonderful. All right, guys. Yeah. Let's resume. Yeah. Weekend internet. I think I have a Netflix problem in my area. Saturday night. So could be that issue. Okay, okay. Let's see now. I've changed my internet connectivity. So probably the different line should be good. Right. So we were loading the stop words, lematizer, converting the raw data to lowercase, and then replacing the quotes, single quotes if you have any. You want to remove those single quotes. So to remove, you are just saying replace with nothing. Identify all the single quotes and replace it with nothing. Yeah. And then tokenizing. So we are taking the tokens. So all your words are tokenized like this, right? And then using this tokenizer, we are generating a text again. So this is your text data. You'll not be able to read it, of course. It's in text format. Okay. Now on this text content that we have, right? Cleanse the data, convert that text one into text content. I've already executed it, so you're seeing the text content already present. But what we are doing is we are further removing the special characters, commas, all these things from the tokenized words. If you see tokens here, it is in a list format. There are full stop, right? There will be uh, probably comma, apostrophes, right? Special characters which I have, all of them are getting cleansed here. So once I cleanse it, I'm getting a little less content. Look at that. It is removing those special characters, right? All the dots, full stops, commas, all of them are removed. Now I'm adding my stop words as a set. right? I have inbuilt stop words. I'm adding those to a variable called stop words. And I'm defining couple of other words as customized words. And I'm adding these customized words along with the stop words here and generating new stop words. So if you see the new stop words, 194 stop words have been created. This is from the inbuilt set of stop words. Yeah. Next, I want to remove the stop words. So compare each and every word from your text content and see if it is present in stop words. If it is present in stop words, then you will be filtering it out. You're not considering it. Consider only if it is not present in stop words. Now, if you see the text content is reduced to 8,775 words only. And on this, further, you want to remove these empty spaces. Right? These were special characters initially. You want to filter that special characters as well. So I remove that. So it is further coming down. 7,478 words are there. Next, on the text content, we want to generate only the unique words. Lemmatization, right? Stemming, lemmatizing. So we were doing lemmatization here. So I cleaned that stem and root words and I found none of the words are having stem concepts. So nothing has changed. But if you have words which are like root and stem logic, stem and leaf logic, then lemmatization would get those words removed. Next, again, I'm defining on this particular NLTK tokens. Tokenizing is being done here. We have already done that here, right, on text data. Yeah, we are not done. Okay, fine. So probably I should have this text content. Let me just do this. Why text content string is there, right? Okay, it's not string. Where is my string? Oh, string is text only. My bad. Sorry. I have to apply the tokenization onto the raw data. So this is giving me NLTK tokens. And then text content, which is already the list of words, right? On this list of words, we are generating bigrams. Take two words together. And if you see those bigrams, yeah, this is the bigram list. Taking two words together and generating the bigram token. Then if you see this bigrams, it's a list, right? It's a tuple. So I'm removing this comma there and adding or generating it as a single string. Right? You put space there and join that and create a bigram list of strings. That I'm calling as dictionary. So now it is not a tuple but a string. Right? Here I'm defining the count vectorizer. Count vectorizer on 2 grams, that is two words together. See how many times the set of two words taken together are repeated. Count vectorizer is basically counting the words on 2 gram. Then apply it based on your dictionary. On the dictionary, you have created the vocabulary. So this is the count that we get it, right? On those dictionary 2 words, we are getting these counts. Now I am generating the sum of these bag of words. Sum of words. Where is that here? So this is like taking each word and seeing how many times it is repeated. Axis 0 means rows. Axis 1 means columns. So you are adding the number of times the word is repeated from row perspective. Sum is applied on row perspective for your bag of words. That basically is looking at the number of times the word is repeated. Total number of times the word being repeated in your entire corpus. And I'm separating the frequency from your sum words. Take the word, take the sum of the words and capture the frequency. From items, your for word in vectorizer, capture only the count. That's your words frequency. Look at that. So you're capturing the frequency, right? Like this. And we are sorting these in reverse order, that is decreasing order of the frequency. If you see word frequency, now the order would be decreased. 1 plus is repeated maximum number of times. Battery life is 16, head jack is 12, refresh rate is 11, so on and so forth. So on that reviews, those are the bigrams that we got. And I'm choosing first 100 words or bigrams. Now I'm generating word clouds here. Words dictionary. This is your words dictionary, words frequency. And the display is 1000, 15,000, and max words you want to print is 200. You're defining these parameters. And for word cloud, you're passing these as parameters here. The number of words you might want to come up with is only 200 words, right? And stopwords is the new stopwords that we defined here, which has 194 stopwords. So it is comparing the words that we have extracted from stopwords and going to print only those words which are repeated. Oops, sorry. In that word frequency, which are not in the stopwords as well. And we are generating the word cloud now. I think I should have said figure 4. Okay, I'll be using this now. Figure 4, title, and show the 4. So I'm putting the black color. 2 words are being repeated together. 1 plus, battery life, much better, wrap charge, headphone jack, screen time, flagship phone, battery drain. Right? So 2 words are being taken together. If you want to do a trigram, you can also take the trigram. You just have to change the number of words that you are going to generate here as 3. Right? So this is about your bigram, friends. So we have generated unigram word cloud. We have generated positive word cloud. We have generated negative word clouds. And we have also generated bigram word clouds. Word cloud, positive, negative, and bigrams. This is in Python. Okay. And we will move on now to R. Okay, break. Yeah, are you sure you want break? Because we will not be able to complete. Okay, we'll do one thing. Too much of coding, we'll take a break. Then we'll come back and discuss about web extraction. That's Twitter data extraction in R. Okay, so the time is 8:36 now. So we will take a 5 minutes break. And come back at 8:42. All right, folks. Yeah, friends, let's resume. Hope everyone is back. So we are now going to learn about how to extract data from Twitter using R. This is the R code. We will have to load tweet R. This is a library which helps us deal with Twitter application from R. Then we have RO authentication. This library is similar to what we have seen in Python as well. This will enable us to actually get the authentication done between R and third-party applications. Then base 64 encoding, this is used for reading the pages, HTML pages, the characters basically. And then HTTP UV is to understand the internet pages, which are internet pages, HTTP pages. Right. There is a scroll. So I have executed all these libraries at one go. Then we have seen the applications, remember? The developer.twitter.com application. From these applications, you would be taking the tokens here from the tokens, copy these tokens and paste it here. Okay, make sure that no special characters, no spaces, nothing are copied here. Okay, so auth factory $new. That's the function. You're creating new credentials here. And you pass these request URLs and access URL and authorization URL here and calling it as OAuth factory $new. This would remain constant. The only things which will change are consumer key, consumer secret key. So we are defining your credentials to connect to your Twitter account from R, right? Those are loaded into this credentials object. We are saving that into a file. I'm calling that file as Twitter authentication.r data. You save it. But where did it get saved? We have not given the complete path, right? So to get that location, here we say get WT. So under my R code folder, I get this R data. Twitter authentication.r data. So we have saved that. So this is only to create your credentials, which will be used for connecting to Twitter account. So I am loading this and then using the consumer key, consumer secret key, then access keys and secret token, access secret token. The 4 tokens which are obtained here are being mentioned here. For different applications, you have different consumer key and consumer secret key. You can also regenerate them. So you might see that this is different from what I'm showing here. If I regenerate it, the values will change. Okay. So I've already used them previously. So still continuing from that same old tokens. Now, when you do it for the first time, when you're executing it for the first time, it will ask you whether you want to connect to Twitter account from R or not. It's confirmation. You say yes. That means select one. When you do that, in the back end, it is going to take that confirmation, and from next time onwards, when you are executing this, automatically it is going to connect. And user timeline is the function. User underscore timeline was the function in Python, tweepy package. Here we are using tweet R package. Under that, we have user timeline function, which is going to capture the data from Virender Sehwag's Twitter page. You can give any name. You can also extract data from Narendra Modi's Twitter page. I've commented it, so it is only executing from this one. And yes, it has executed. You can do a question mark of that user timeline in R. It gives you the documentation if you want to further read about it. This is the syntax that we can pass. And yeah, this is username basically. N is the number of tweets to retrieve. Up to a maximum of 3,200 tweets can be retrieved. Right? So when I put 1,000, it is not capturing all the 1,000. It is capturing only 442 tweets. Just like how we have a challenge with Beautiful Soup package, Twitter R package is also having the same issue. It's not able to extract complete details. Now, this is in the list format, mind you. It's not in a data frame format. So you cannot just say tweets to see it. If you say this, it will not basically show it in a proper way. If you want to see each individual result, then you have to use this double quotes and mention the number of that particular tweet. So if you say 442, it will get only this Twitter, that status. I'm saying tweets 1. This is the first tweet in the Virender Sehwag's page. Let's go back to Twitter. And let's search for Virender Sehwag's page. Yeah, this is the first tweet. Yeah. So a young boy called Harish from Barmer in Rajasthan climbs a mountain every day, so on and so forth, and that's exactly what we got. Right? Now I want to convert this into a data frame. It's not in a data frame. Yeah. So let us execute this. This is an inbuilt function which is there in tweet R package, which is going to convert the list or the tweets that you have extracted into a data frame. Tweets data frame. Once it is in a data frame, you can see there are 16 different columns. Right, our tweet userline function is actually capturing. A lot of such details are captured here, right? We are interested in this text. We can only select that text and save it, or you can save it directly, the entire data into a CSV format or in a text format. If you want to write it into a text format, then you would say write dot. If it is in Excel format, you would say write dot XLSX. So I'm saving it in a CSV format, and this is getting stored in the same location here. Tweets.csv. Let me open that file and show you. Yeah, this is your tweets data. Now, on top of this Twitter data, you can perform the word clouds. We will be probably doing that exercise tomorrow. Write dot table will give us a text file here in this location. This is in a text file. Of course, text file does not give you in a proper format. So this is how you extract the data from Twitter and store it into your system for further processing. Yeah, so this is basically the Amazon extraction. Here I have Twitter extraction, right? And we can also use the same code. Let me, okay, use this file.choose to load the data. Let me load the CSV data here. I'm calling it as X, and it is a character with, okay, let me just take text data. Okay, it would be really clumsy otherwise. Oh, it's open, so let me close it. Yeah. Now let me load the data so that I get only text data. I don't get all the data, right? But if you see, there are a lot of junk characters also coming in X. We'll have to cleanse that. So let me first load string R, and then let me load text mining package TM. These are the two packages which are required for you to load the data, cleanse the data. And here, replacing all special characters with space. First thing, replace all that special characters which are there in X, right? All the graphs that you see, right? The emojis and all those things will be removed by the space. Then I'm loading this character data that we have into something called as corpus. This is required for dealing with our R. So it is going to convert that character data into a list of data, right? X1. And then I'm applying the bunch of pre-processing steps. Convert everything into lowercase letters, remove the punctuation marks, remove numbers if there are any. And then in R, we have inbuilt stop words as well. In R also we have that. And these are 174 words. 173, 174. So I'm removing these stop words from X1. And what happens when you remove? White spaces are created, right? Then we are going to load that data after removing that extra white spaces which are created. Then we have this library called word cloud in R. I'm loading that and simply say X1 cleanse data and pass the word cloud function with the bunch of parameters. The colors would be blue. The random order is false. That means you take in a specific order that the data is passed into. Minimum frequency is 10. That means don't go below the word which is repeated less than 10. These is your word cloud in R. Different font sizes, different frequencies. All right, so we'll stop here. Tomorrow we will look into the Amazon data retrieval, and then we'll perform the word cloud. Then we'll also do bigrams. We will also have something called as word cloud 2, which gives us different shapes. Here it is just in a random shape, right? We'll also arrange the data in different shapes. Bigrams will be constructed, and we'll also do very interesting thing, which is basically the comparing the words. So let's say you want to generate word clouds, right? And compare two products. Competitor analysis needs to be done. So we will be able to do that using this particular comparison cloud, right? So all these things we will do in the next class, that is tomorrow. And then we'll also have the NLP concepts where LDA will be performed, right? And we'll also do Fourier transformations. We will do emotion mining, okay? And we will generate visualization, a bar graph which talks about different emotions, let's say on a product, whether the product is being loved, whether the product is hated, anticipation, angry, disgust, like this, different emotions can be captured. All right, so exciting things in R tomorrow. Let me take your questions. Tushar, the codes, few of the codes are uploaded, and yeah, these codes that we are discussing, they will get uploaded into your R codes are already there in LMS. You can probably look into that. Is the problem with the size? Can you break it up and make it more efficient? What do you mean by that? Pranesh, you can try and do that. There are certain attributes that we can pass into the function. We cannot just pass it at one go, right? I mean, the functions are defined to do something, certain things. You cannot do batches wise. It takes user timeline is a function which takes the most frequent, or sorry, most recent timelines or statuses. This is one way. User timeline is one way to extract the data, which is popularly used. You can give 3,200 and see what is, how many reviews it is getting, how many status it is extracting. There are certain issues with these functions that we have to live with, unfortunately. Yeah, Sheikh, I've already passed your number. You will be added into the group. Probably today you will be added into one of the groups. All right, friends. So I will get these codes uploaded, LDA, LSA codes as well into your LMS. You can just go through them, run through these codes. And coming to the data, yeah, data sets will also be uploaded, but I would try and give you smaller data set for practice purpose. Okay, once you're comfortable, probably you can explore more on the data. All right, guys, so let's connect again tomorrow. And trust me, tomorrow it would be more fun because it is R, right? So see you guys tomorrow. Yeah, thank you, friends. See you tomorrow. Bye.